Hey everyone, my name is Dan, and in this video, I'm going to walk you through how to perform a meta-analysis of mean differences in Jamovi. Jamovi is a fantastic open source and free piece of software that allows you to perform statistical inference, and most importantly, it allows you to perform reproducible statistical inference. There are plenty of options out there available for performing a meta-analysis, but many of these options, particularly the more popular ones, are expensive, and these aren't easily reproducible for other people if they want to try and reproduce your meta-analysis. So Jamovi provides a fantastic alternative, and there's a particular Jamovi module that allows you to run meta-analysis. And this module, which is called the major module, is a wrapper or an implementation of the popular metaphor package in R. But if you are not comfortable or familiar with R, then Jamovi, or the major module within Jamovi, provides a great way for you to do this meta-analysis. So let's have a look at this data set. Within this data set, we have 9 studies, and these studies are comparing outcomes for specialized stroke treatment versus routine or normal stroke treatment. And with these particular studies, we have the outcome measure is number of days. The most ideal thing is to have the least number of days within hospital. So the hypothesis for this particular meta-analysis, or for the studies included within this meta-analysis, is that specialized stroke care leads to reduced days in hospital. So we have a number of studies here, and we have one variable, which is the number, one, which is the standard deviation, one, which is the sample size, and then we also have our control groups. So this is the number in the control, the number of days, standard deviation, and the sample size within that control group as well for these particular studies. So to run this meta-analysis, we click on the major module up here, and we want to look at mean differences here. So within Jamovi, we have a number of different things that we need to actually tell Jamovi in order to run the analysis. Remembering, we want to have our group 1 sample size, which in this case is the participants who had the specialized stroke care. So we have our group 1 sample size here. This variable, which represents our group 1 mean, remembering this is the number of days. We have our group 1 standard deviation. And now we have our group 2 sample size, our group 2 mean, and our group 2 standard deviation. We also, in order for this analysis to run, we need to specify a study label. So if you are collecting your own data and including this as, say, a CSV file for your data, then you would have to specify a study name. This could be a number, or it could be the first author of the study. In this particular case, this is a number. Now, for this particular video, this doesn't show you how to extract data or other important things for meta-analysis, which include pre-registration. I have a number of other videos which show you how to do that, so make sure you check those out on my channel. But for this particular video, this is just looking at how to run the analysis, assuming you already have the data. So Jamovi has already run this particular analysis. And the great thing about Jamovi is that it provides text output for you. It provides your results, which is fantastic. So as well as actually giving you the meta-analysis output, it describes the analysis that was done. And in this case, this uses the default. So let's have a quick look at what we found here. We can see with this particular analysis that this was not statistically significant. So assuming you're using a p-value threshold of 0.05 to represent statistical significance, in this particular case, there was no significant difference between the specialized stroke care and the treatment as usual. So we can see what the what the estimate was, the p-value here, and also the heterogeneity statistics. So in this case, there seemed to be, or the Q test for heterogeneity statistics suggested there was high heterogeneity, or there were high differences between the particular studies. So we can see all the output here and how this analysis was run. We can see the number of studies that are included, and the range of mean differences. There's a lot of really interesting information. Now, for your particular analysis, you may or may not want to include all this analysis in your output, but there's a lot of interesting stuff in there. We also have our forest plot, which visualizes the results of our meta-analysis of mean differences. And we can see our analysis suggested there was high heterogeneity. And we can see here there's quite a big difference between the studies. With these forest plots, the size of the square here represents the amount of contribution the particular study, or the contribution of the study for the summary effect size. So studies which have lower variances, as in studies which had larger sample sizes, contribute more to the overall summary effect size here. So this study 1, for example, contributed a lot because its variance was quite low, whereas study 5, for instance, only had a small contribution because its variance was quite high. So looking at the individual studies, there was a range of results here. None of the studies actually suggested that the routine care had significantly more days in hospital, or the people that receive routine care. However, there was a number of studies here which suggested that the participants that received specialized stroke care spent significantly less days in hospital, but there was quite a range here. Let's have a look at model options. When you're running a meta-analysis, you have a number of different options for your model estimator. The Jamovi major module by default uses the restricted maximum likelihood estimator, which is a good all-round estimator. However, another potential or common estimator is the Dersimonian-Laird. So if we can choose that, we can rerun the analysis. And what's interesting is that when you rerun the analysis using that particular estimator, the results are statistically significant. Now, overall, this would suggest that for this particular data set, it seems to be quite sensitive to the type of estimator used, which suggests to me, if you were running this analysis and you found a significant result, which was just under the threshold of statistical significance, this particular result isn't terribly robust because it seems to be sensitive to the type of estimator used. So if you're not sure so one good way of testing the robustness of your analysis is to try to see whether this actually holds for different types of estimators. But the two most common estimators used, at least within the biological sciences, are the Dersimonian-Laird and the restricted maximum likelihood estimators. But in this particular example, it seems that the statistical significance actually depends on the type of estimator that is used. We're going to go back to this because we can do some interesting analysis with this non-significant test. So let's have a look at some of the plots or some of the options that can be used. We have a number of options that we can adjust for our forest plot. So you can actually change the type of here we have diamonds that are used for the effect size points, but it is quite typical for the summary effect size to use a diamond. So I think it's a better option to use circles or squares to better differentiate between the individual studies and the summary effect size. And you can also adjust the size of the forest plot as well. If you right-click on the actual plot, then you have options for exporting the plot as well. So you can export it or you can copy it. So when you're actually reporting your meta-analysis, this is how you can change your forest plot. Like I said before, this major module is an implementation of R, and you're not going to get the same amount of options that you get when you're using or doing meta-analysis in R. Plots are highly customizable, but you do get a fair few options. So if you're looking at this plot thinking, oh, I want to change a few different things, and you can't do that within Jamovi, then maybe it's worth investing some time in learning how to do this in R. However, you do get a few good options here as well. Another thing you can do is, what is quite standard to report, is a funnel plot, which plots a measure of variance, in this case standard error, against the measure of an effect size here. One reason that we do look at these forest plots is to see whether there is funnel plot asymmetry. which is one way to look at whether there is a evidence of small study bias. Now, small study bias is often confused with publication bias. And publication bias is certainly one part of small study bias, but one of the most common misconceptions that I see within meta-analysis is papers that are reporting funnel plot asymmetry as a measure of publication bias, when this is actually a measure of small study bias, which can include publication bias along with a few other things as well. And there's a few different options we can do with our forest plot. One option that I really like is this contour enhanced funnel plot, which visualizes statistical significance. So if you have a lot of studies which are falling within these particular contour plots, then that would suggest that there may be an overrepresentation of statistically significant studies, and that there was a number of studies which weren't published because the results were not statistically significant. So we have a few different options here, but I think the contour enhanced funnel plots are a good way of visualizing publication bias. But of course, this can be quite subjective. One person may look at a contour enhanced funnel plot going, well, there's a lot of studies in these contour plots. Maybe there's a high risk of publication bias, whereas others may look at that going, well, I don't think so. It doesn't seem like there's an overrepresentation of studies. There are a few options for more objectively looking at publication bias. Now, remember, funnel plot asymmetry, whether you're using a measure of Egger's regression test, which is a common way of visualizing or of looking at funnel plot asymmetry, is not a measure of publication bias. So we can see here within the publication bias assessment, we do have Egger's regression test. So Egger's regression test specifically looks at funnel plot asymmetry, and here the test was not statistically significant. However, that is one way of doing it. But again, this is looking at small study bias, not publication bias. There are a few different ways that we can look at publication bias, a few different methods. A number of different methods are available. There's not one method which has come out to be a clear winner on which is the best method. So what is often recommended is to apply a number of different methods to see if there is consistency between methods. So if you're trying 3 different methods that specifically look at publication bias and they all point to publication bias, then you have some good evidence there. However, if 2 methods say there is evidence of publication bias and one doesn't, maybe this result isn't so robust. So to give an example, one thing we can look at is selection models. Now, selection models, these models assume that studies which are statistically significant are more likely to be published, whereas studies that are not statistically significant are less likely to be published. So what these selection models do is that it actually increases the influence or the contribution of studies which have p-values which are less likely to be published. So if there's a p-value of 0.4 and that study is in the meta-analysis, that study has a greater contribution within the meta-analysis compared to a study which is statistically significant, so it has less influence. So it selects for studies depending on the likelihood that they're going to be published. So that's one way of looking at publication bias. Here, this also suggests the p-value is 0.32. So this suggests that once you adjust for the likelihood of whether a study is going to be published or not, that here there is there's no evidence, at least according to this test, of publication bias. So if we're just using this test alone, this could be evidence that, hey, there probably isn't publication bias within this particular example. Let's go back to our model estimator, and let's just say we were sticking with a restricted maximum likelihood estimator. And remember, for this particular estimator, this was not statistically significant. The p-value was 0.082. When you have a result that is not statistically significant, there is no way of knowing whether this result is actually evidence for equivalence or evidence for a null result or simply data insensitivity. There's no way of knowing this. Of course, there are ways of doing this. If you take a Bayesian meta-analysis approach, you can actually look at the relative evidence for a null model versus alternative model. I do have a video on how to perform Bayesian meta-analysis, so you can check that out if you're interested. However, there is a way of looking at this within a frequentist framework, and that is by doing equivalence testing. Now, equivalence testing was first developed in the 80s for looking at pharmacology studies, but it has become more and more popular within psychological sciences as a way to evaluate evidence for equivalence for non-significant tests. This is included as a feature within the major module. So let's go down and show and run this equivalence test. So for this particular equivalence test, by default, it assumes that studies that have a Cohen's d between minus 0.05 and 0.05 are essentially equivalent, or they're statistically equivalent there. So effects that are within these particular bounds, so you can see these bound here of minus 0.5 and 0.5, these effects don't mean anything. So although there might be differences, or there might be an effect, that these effects don't really mean anything. In this particular, so for this particular study, as you can see here, these the 90% confidence interval, which is this bound here, was not significant. So this 90% confidence interval fell outside this 0.05 equivalence bound. Now, of course, you can change this. So let's just say that we would assume that effects that are within minus 0.2 and 0.2 are equivalent. Seems like this hasn't adjusted yet. Here we go. There we go. So even if we would assume that for these equivalence bounds to be very, very small, this equivalence test is still not significant. So this shows us, remember the equivalence bounds are 90% confidence interval. So this is the this is the thick line, whereas the traditional 95% confidence interval is the thin line. So here, because the thin line crosses 0, the traditional test is not significant. So this is the result that we have above here. But the thick line also does not fall within these equivalence bounds. So not only is this test not significant, it is not only is the traditional test non-significant, the equivalence test is also non-significant. And this is due because as you can see here, the variance is quite large. And when you have large variance, it's very hard to make solid conclusions. And the reason being is that the sample sizes for this particular meta-analysis were quite low. So we can't determine significance either using our null hypothesis significance test or for our equivalence test either. Now, of course, if we really make our bounds really big, this is unrealistically big, but I'll show you for the case of demonstration here. So if we were for some reason to say that Cohen's d values of minus 0.15 and 1.5 were considered equivalent, and there's very few areas of research where that would be a reasonable assumption, here we can see that the effects are statistically equivalent. So it is up to you. There is no rule of thumb for what is equivalent. This changes from field to field, but of course, quite often you need to have a starting point. Maybe you genuinely don't have any idea for what is considered equivalent. So one thing you can fall back on is Cohen's guidelines for what constitutes a small, medium, and large effect size. But again, these are just guidelines for when you have no idea. So I'd say for most areas of the biomedical sciences, using a threshold of minus 0.2 to 0.2 is a pretty decent starting point for equivalence. That is, if you have no idea for what represents equivalence, and you would simply report that is what your equivalence bound is. Finally, I want to show you influence diagnostics. So these are ways of seeing, is there a particular study which has an outsized influence on the overall summary effect size? This runs a number of different tests that look at influence, look at the documentation of the metaphor package to get a better understanding of what these tests all represent. But here, any study which has a red dot is indicative of a study which has an outsized influence on the overall summary effect size. So for a number of these tests, it looks like study 3 almost always shows considerable influence. So let's look at study 3. And yeah, again, this is that one study which had a really large effect size and small, so an effect size of 0.23 and quite small variance as well. So it seems like for that particular study, it seems like it has an outsized influence. If this was within within Metaphor, I would run what's called a leave one out analysis, where I would run the analysis again without this particular study. And this is another test of robustness. If the outcome relies on a single study, then perhaps that study, or perhaps the meta-analysis isn't terribly robust if the result or the conclusion depends on one particular study here. Although I'm not going to do it, I'm fairly confident that if you were to remove this study, then this result would be, the summary effect size would be shifted much more to the right. So it seems to be sensitive to one particular study. So that is how to run a meta-analysis of mean differences within Jamovi. I hope that is helpful.